Hey everyone, so in this video we're going to be going over Atwood machines. Now the neat thing is you actually already have experience with Atwood machines, you just don't know it. And the reason being that an Atwood machine really is just some kind of device that shows the relationship between acceleration A. So it shows the relationship between A and forces, so F. So it kind of shows the relationship between A and F, when hopefully that has to do with M, because we know Newton's second law is F net equals MA, right? So that's hopefully kind of the connection here that we're getting today. And the real idea with that is it consists of two masses, at least two. So there's a lot of cases where there's three or four even. And at least one is hanging vertically from a frictionless pulley of negligible mass. So we get to ignore friction, we get to ignore the mass of the pulley. And another really important thing here is they are unequal masses. If they're equal masses, well, we typically don't get exciting stuff, really. Okay, but that's kind of the idea. And so we kind of have a little image here of an example one. And this is, hopefully this kind of jogs your memory, this is the ticker tape timer lab from last unit. We actually have already dealt with this, where we had the little green cart, and the green cart ended up sliding down kind of the table, the countertop itself, as the ticker tape timer made all those dots on the paper. And it's because this little mass at the bottom, in my case, was a 100. Usually we'll use a 200. Sometimes we'll use a 300. That mass is going to pull it over the side. And so if it wasn't for this little hanging mass, the cart really wouldn't go anywhere. And so it's this one little mass is actually pulling not just itself, but this cart's mass as well along the counter. So we have kind of a smaller net force pulling this larger mass, and it's kind of a kind of unique setup here. And so that's really it. And so what I've done is I've just kind of outlined a kind of simple, easy one here. And I've also kind of gone and done the little free body diagram on both of these parts of our system, the system being both of these different objects with mass, where again, we're ignoring the mass of the string, we're ignoring the mass and any friction in the pulley here, and we get to assume that like the strings are unbreakable, which is a pretty neat, convenient assumption to make, absolutely. And so really, if we look at this one, we can see that the net force on the cart is really due to the force of gravity pulling down on mass 2. If this mass wasn't here and this countertop was actually flat, well, we would end up just having the cart just sitting there doing a whole lot of nothing. So it's kind of neat because the net force is due to M2, but really it's acting on this entire combined mass of M1 plus M2. So that's kind of the unique aspect of the Atwood machine here, is you have only a portion of the total mass is causing the net force that then accelerates this entire system, is kind of the whole idea, okay? And so what we can do here is we can look at this one and go, hey, well, we just said that the net force, well, it's the total mass that's moving, because everything is moving here. Everything is accelerating, right? As this little mass starts going down, well, this cart is going to start going this way. And so every little bit that M2 accelerates is the same amount that M1 accelerates. And so we can see here that, well, the net force is equal to this total mass that's kind of accelerating times this acceleration. But we also have kind of come to an agreement that the net force is only caused, the thing that's actually moving and accelerating this whole system is really just due to the force of gravity on the hanging one. The force of gravity on the stationary cart doesn't do anything. It's being opposed by this normal force right here. So that doesn't actually really do anything for us. And so it's kind of neat because we have the net force is equal to M2G here, but also equal to M1 plus M2, all in parentheses, times A is the whole idea. And so the neat thing is, since these left sides are equal, I can set the right sides in pink equal to each other. And so that's exactly what I did. That's what I have here with my M2G. That's kind of this side, and that's equal to kind of this whole portion. And so with that then, typically with an Atwood machine, you're either being asked to solve for what one of the masses is, or you're being asked to solve for what is the acceleration of the system, or what would be a symbolic equation that kind of represents the acceleration of the whole system is the idea. And so if I kind of get it in this format here, well, then I can just divide by m1 plus m2. And so really, we kind of get this kind of final formula here for at least this scenario, going that, hey, well, we can see here that the bigger M2 is, so the bigger this guy is, the bigger A will be. And that should make sense. If you have a bigger, heavier thing hanging here, well, everything is going to go faster kind of as it moves, right? So that hopefully kind of is intuitive. But now we're kind of looking at the math and finding reason and kind of explanation from the math. We're kind of reading the equation, going that, hey, well, if this mass goes up, so does the acceleration. If gravity was somehow increased, so too the acceleration. So if you took this to Jupiter, where gravity is much stronger, it would accelerate faster as well. And this also tells us that if the bigger M1 gets, the smaller A gets, because if I have a bigger thing in my denominator, that means this whole fraction is kind of going to become a smaller value itself. So that's kind of a neat thing that we can kind of get a good conceptual understanding of like what's happening with this whole system here based on this equation we got by looking at Newton's laws and what's kind of the net force at play here. Okay, so here's a little bit more of a complex one. So I want you to actually try and do the same steps I did here, okay? And what I'll say, that's kind of a tip that we'll have to start doing with these Atwood machines. We'll start solving these kind of in the coming days, is that you actually have to pick a direction and be positive. It really doesn't matter. I could have totally gone and said, forget that one. I want positive to be, ooh, that's a terrible plus sign. I want positive to be that way. You can totally do that. You need to keep in mind then that if positive, and I'll get rid of it, in my case right now, if positive is going kind of clockwise that way, well, that then tells me that this force gravity on mass 3, that's in the positive direction then, right? But that also tells me then that force gravity on this first mass is actually in the negative direction, okay? And so I know that's kind of this hopefully is a little bit of a challenging one. But again, kind of treat it the same way as I did here, and then you can kind of just set things equal, all right? Now, the neat thing is I have not told you if M3 is bigger than M1 or if M1 is bigger than M3. And I'll give you a hint. You'll need to use kind of absolute value bars there, okay? But that's really it for kind of the gist on an Atwood machine. We'll have another video that's really some more in-depth steps on how to really attack these. That'll include some sample problems that we'll kind of go through together.